Okay, guys, good morning. We have about a minute for the top of the hour. Any questions before we get started? Question?
On the lab report, do you want us to explain the mechanism or just have it on there?
First off, I'd read the directions. Because whatever I say doesn't count. What the directions say is what counts. Because I sometimes may not remember or say something incorrectly. Typically, though, if you want to give a mechanism, it's probably a good idea to discuss it just briefly. Other questions, guys? Okay, we will have a quiz on this Friday. Everything up through where we are now, including mass spec. Quiz on Friday. Lab this week, turning in your group report, and we'll have some type of lecture downstairs, meet downstairs. Yeah? Everybody good? Okay, substitution reactions. We continue along. Okay, we did a reaction here, a substitution reaction. Importantly in this reaction, if we start this oxygen here, where's the oxygen now? The oxygen is now here. This oxygen is new, okay? Please recognize that. That oxygen came here. We replaced the OH with the methanol. We lost the proton, okay? We lost the proton here. Proton got lost. That's all in your mechanism, though. And the leaving group here was water, not hydroxide. We protonated the oxygen, we made it a positive charge. Okay, these other atoms, if we make them a positive charge, then they can leave. Okay? It will not leave on its own. There's no acid here. Here we have a strong acid. Okay? Strong acid to protonate. Classical way to make an OH, or any oxygen really, any oxygen a better leaving group, make it a positive charge by protonating it. We said this reaction is no good because you can't have your cake and eat it too. You can't have acid and base in the same reaction. This is just like hydroxide. OH, OMe, they're both anions, they're both bases, same thing. You can't have hydroxide and H plus in the same reaction. You can't have methoxide and H plus in the same reaction. So in the previous example, we had to use the neutral nucleophile. Okay, the same idea here can be applied to halogens. Very common to react an alcohol with HX. Okay, HBr, HCl, and we can replace the OH group with a halogen. This supplies the H plus. It also supplies the nucleophile. Note in this case that we can have I minus with H plus. So that's almost by definition. Halide anions can exist with H plus. I mean, that's how HI exists when ionized. You can have both of these. You cannot have both of these with the oxygen. But this allows us to do the reaction because we have H plus. Protonate the oxygen, They bond to oxygen, 1 lone pair left, that's a positive charge. Then the I minus that's here, these electrons come in here and do a backside attack, inserted SN2, kick that off, and there you go. You get the iodide on the carbon, tetrahedral carbon, and then the water was the leaving group here, yeah? SN2, yeah? SN2. That's a very common reaction of alcohols, reacting with HX to give the alkyl halide. Okay, in addition to OH groups, OR groups can also leave. That is, it doesn't have to be an H on the oxygen for the oxygen to leave. It could be an R group. Let's show the product of this reaction. You want to work mechanistically, just like if you're doing a math problem. You have like a formula or an approach in math. Your mechanism, again, is how you figure things out. What chemistry do you know? What can happen? We're never going to react anything in this class, in this organic one. Never react to benzene ring. No benzene chemistry in this class. Alkane. Alkanes have no reactivity. What's the first reaction you see here? Anybody have products here? And then what? And then what? It leaves? I don't think it's going to leave. So you did an SN1 mechanism?
No,
Okay, it inserted, it's kicked off. Okay. And the products here are those two there. How we doing? Very good? No? Get something different? What'd you get? BR attached to the benzene ring. Plus what? What's that? No, nobody does. First thing we do is protonate the oxygen. Can I just protonate it without doing that as a mechanistic step? Now, on the quiz or test, you have to do a mechanistic step. But we're going to protonate things probably 50 times in the next 2 weeks. If I have to protonate every single time, that's going to waste 50 minutes. Can everybody protonate an oxygen? You promise? We did it a couple of times. It's just an acid-base reaction, just like we learned way back when. There we go. All right? We got Br minus. First off, we've made the oxygen a good leaving group. That's what protonation does, right? Makes it a good, better, good leaving group. Now these electrons come in here, attack the carbon, and kick off the oxygen. And when you do that, you get those products right there, right? Oxygen bonded to carbon. Now bromine bonded to carbon. What did we do wrong?
I did a bromine attacking the other side.
So you attack this carbon, kick the oxygen off of that carbon.
Yeah.
That ain't a tetrahedral carbon. Make sure you note the heading of this. Back to the beginning. What's the heading say? Nucleophilic substitution of what type of carbon? Tetrahedral carbon. Chemistry we're doing only takes place at tetrahedral carbons. Carbon that you attacked and kicked off the leaving group is not a tetrahedral carbon. But the leaving group was attached to two different carbons. But it's only going to leave from the tetrahedral carbon. Now, did we do the right mechanism? I did an SN2. I did an SN2. It's somewhere right there. Right? SN2? Or should we have done SN1 here? Okay, let's look at another way to do B. What was A? What are we under? Sounds like we're under some headings. What are we under?
Making oxygen a good leaving group.
Making oxygen a good leaving group. What was A? Protonated. B, another way to make oxygen a good leaving group is to convert it to a tosylate. By the way, you would never do SN1 up there because that would involve a primary cation, and we don't make primary cations, right? Good. Okay. Another way to make OH a better leaving group is to convert it to a tosylate. Tosylate is the one you'll find in your book. Also, mesylate or triflate. These are very analogous. They're just a little more advanced and maybe not in your book. Same thing though. Same idea. A tosylate is this guy here. First off, tosylate is short for toluene sulfonylate. Toluene. Toluene is a benzene ring with a methyl. You put a methyl on benzene, it's then called toluene. You can buy it at Lowe's in the paint section. Toluene. Toluene. SO2 is sulfonyl, so that's toluene sulfonyl. And it's the oxygen anion here, or when it's an anion, kind of 8. Toluene sulfonylate, shortened to tosylate. It's when the oxygen is bonded to the SO2 toluene. Tosylate is abbreviated, it's strictly abbreviated OTS. I abbreviated TOS, OTOS. But officially there's no O in between. Okay. But I like to be able to say OTOS. So that's how I abbreviate it. The whole thing here is to tosylate. Not an OH, but an OSO2 phenylmethyl. The tosylate will serve as a leaving group without being protonated. Just like a halogen will serve as a leaving group without doing anything. A tosylate, because it's like a halogen in terms of leaving group, is often called a pseudohalogen. And so we can get nucleophiles to come in here and this oxygen will just leave. It's a good leaving group, as is. We'll see how to make these in just a minute. So why is this a good leaving group? What would this give? We would then have the nucleophile bonded to our tetrahedral carbon in place of the leaving group. But what would the leaving group look like? Oxygen has two lone pairs, right? The oxygen left. And how many lone pairs on this oxygen now? 3. And what's the charge of this oxygen now? Yes, negative. This is generic for just some aromatic group. Okay? What is the aromatic group? It's a benzene ring with a methyl on the end. You need to know what tosylate is. That's just generic. Maybe like a phi, Phi-5-O. Okay. Earlier we said that an OH minus will not leave. Why will this leave? Why is this? That implies that this is more stable. Why is this more stable than that? Why will it leave? Any stability here compared to that? Yeah, you got electronegative oxygens. What's the big thing here, though? Somebody said? Resonance. Yes, resonance, right? In, out, right? And you can draw resonance. We can put the minus on this oxygen. You can also put it on that oxygen. It's resonance. Okay? It's a resonance stabilized anion. A lot of resonance. Charge can be localized on 3 different oxygens. You've also got an electronegative sulfur there that's more electronegative than carbon pooling. This is a good leaving group. Tosylate, good leaving group. Don't have to do anything to it. There's variations of this. Instead of a toluene over here, if you just have a methyl group, that's called a mesylate. A methyl sulfonylate. Mesylate. It's the same idea. It's just less common at the introductory level. This one's particularly good with these fluorines out here, which really cools and really stabilizes the anion. Trifluoromethyl sulfonate. It's called a triflate. Very good. These are a couple of sort of variations, very important though. This is the dimethyl ester of sulfuric acid. If these methyls were H's, that would be sulfuric acid, H2SO4. So the H, if we have a methyl, I can actually call it a sulfonate ester. Just like if we went from, that's a carboxylic acid, right? With the carbonyl OH. It's the SO2OH, but if we change the OH to a methyl, that's now ester. Well, this is a sulfate ester, or sulfonate ester, from the sulfuric acid, or the sulfonic acid, on both sides. But the same thing here, the nucleophile may or may not be minus, can attack this carbon and kick off this oxygen. And you can actually attack on either side, but it usually only supplies one alkyl group. Now this is just going to supply methyl. This is called, what's the name of this compound? Well, what's that called? What's this called? You use it to dry your extracts with?
Sodium sulfate.
Sulfate. Sulfate. Well, if we put methyls on sulfate, which is now that, what is that called? That's right, dimethyl sulfate. Okay? Dimethyl sulfate. It supplies a methyl group. It's an electrophilic source of a methyl group, which is an alkyl group. It's an alkylating agent. It supplies an alkyl group, methyl. But you can also have diethyl sulfate. Right? And it would supply an ethyl group. We can attack carbon. You would end up with an ethyl on your nucleophile. These are very common because they're very cheap. They come from sulfuric acid. And you can get a gallon of these for pretty cheap. Problem is they're very toxic. Especially dimethyl. I mean, that is too. But this is even more because it's a very, there's no sterics here. Good leaving group, no sterics. Same thing like this. I mean, if we have methyl iodide, these are analogous. A CH3 with a good leaving group. CH3 with an iodine. Both of these very toxic. Okay? Because your DNA will attack this and kick off that leaving group. Proteins, nucleophiles all in your body. But we will be using this in lab when we come back for reacting with acetaminophen. So, same idea, it's just it's sort of symmetrical, but typically you're only reacting on one side. Same as this. I mean, that could be an ethyl group. Here, the other side is inert. Okay, how do you make tosylates? Tosylate here would come from the alcohol. Okay, we got an alcohol. We want to replace the OH group on this carbon. Do some substitution on this carbon. How can we make this a better leaving group? We can protonate it. That would require us using some acid. Right? We did examples up there, like with HBr. We can get a bromine here, mechanistically. Another thing we can do, though, we can convert it to the tosylate. First, that would be done reacting with tosyl chloride. The SO2 with the chlorine, and then like the toluene here. I'm not going to go through this mechanism because it's not SN1 or SN2, but it is substitution. The oxygen replaces the chlorine. But that's not anywhere near a tetrahedral carbon. It doesn't matter if it's carbon or not, but it's not tetrahedral. It's not going to be an SN1 or SN2. The oxygen replaces the chlorine. Right? Under my hand's chlorine. That's oxygen. And the oxygen has an ethyl group, that's always going to be there. If we balance this out, I'm not going to do mechanism here. You'll see an organic 2, I covered at the very beginning of organic 2 when we do that type of chemistry a little bit. What's going to be the byproduct here if we fully balance this? That plus what? One molecule form. HCl. Yes, that's it. The H and the Cl. That's okay. Because HCl being formed is usually not good, very often you include a base here to react with that HCl. So maybe you use something like pyridine. Pyridine is a benzene ring with one nitrogen, one lone pair, and that is a common weak base. That's often included to react with acid that would be formed. Again, I'm not showing mechanism, but this is tosyl chloride.